Thank you very much, and welcome back to the dimensional analysis hydraulic similitude topic. In the previous module of the dimensional analysis, we have understood about what is the dimension and what is the importance of dimensions, and what is the difference between a dimension and a unit, and most importantly, dimensional homogeneity. Which equation is considered to be dimensionally homogeneous? Which equation is considered dimensionally non-homogeneous? There are two methods for making use of this dimensional analysis technique for solving the fluid flow problems: Rayleigh's method and Buckingham Pi method. And in the previous module, we discussed about the Rayleigh's method of analysis. Okay, so in the Rayleigh's method of analysis, the basic principle that was used was that a functional relationship can be established between the dependent and independent variables. This functional relationship can be transformed, converted into an exponential equation by multiplying all the dependent variables, raising to the powers of different exponent variables. Different exponent variables. Okay. Different exponent. This is how probably the Rayleigh's method has become a very powerful tool for getting the solution for several fluid flow problems. We have taken up one problem or two problems. One is on the torque and the other is flow through an orifice, discharge equation through an orifice. Okay, and we try to take up the second method, Buckingham Pi method, today, and try to compare these two. What is this Buckingham Pi method? So this is Pi. You can see here it is the Buckingham Pi method. Okay, so the Buckingham Pi theorem states that if there are n-dimensional variables involved in a phenomenon, which can be completely described by m fundamental quantities or dimensions. What are the fundamental quantities? Mass, length, time. Temperature, of course, for the other types of fluids where we have a change in temperature also. Otherwise, mass, length, time are treated to be the primary quantities or fundamental quantities. Mass 1, length 2, time 3. So you have total 3 primary quantities are fundamental quantities. So this m refers in this Buckingham Pi theorem m number of fundamental quantities. That means mass, length, time. Suppose if the entire physical phenomenon is completely described by either with mass, length, and time, these 3, then the value of m becomes 3. If the entire physical phenomenon is described only by 2, say length and time, then the value of m becomes 2. So this is how m fundamental quantities or m primary quantities may be either 2 or 3 or 4 depending on the physical phenomena that is selected, and n variables are there in a phenomenon. Total number of variables available are n, dimensional variables are n, and all these n variables are completely described in terms of the primary quantities using m primary quantities, 3 or 2 or say 4. So m fundamental or primary quantities and are related by dimensionally homogeneous equation. Then the relationship among the m quantities can always be expressed in terms of exactly n minus m dimensionless independent pi terms. This is what the Buckingham Pi theorem statement, which gives you there is a physical phenomena. This physical phenomena is completely described with n dimensional variables, and these n dimensional variables, when you start writing the dimensional formula, you have used m primary quantities. Then if they are dimensionally and they are related by a dimensionally homogeneous equation, then the relationship among these m quantities can always be expressed by n minus m dimensionless independent pi terms. So you have n variables involved in a phenomena, m primary quantities which are available, then n minus m becomes the dimensionless term. These dimensionless independent terms are called pi terms. Pi terms. Okay. This is what the Buckingham theorem. So what is the methodology? Mathematically, if any variable, say q1, which depends on the independent variables q2, q3, q4 up to qn. So you have dependent variable, independent variables in this. Dependent variable is q1. q2, q3, q4 up to qn are the independent variables. Then a functional relationship between the dependent and independent variables can always be established by using this functional equation, like q1, the dependent variable, is equal to, which depends on q2, q3, q4 up to qn. So f of q1 is equal to function of q2, comma q3, comma q4, and so on qn, and so on qn. So this is what is the functional equation, or the functional relationship between the dependent and independent variables. This can be transformed to another functional relationship. The second, another functional relationship is another function f1 of q1, comma q2, comma q3, comma q4, and so on qn is equal to a dimensionless constant c. A dimensionless constant c. So what has been done here? The dependent variable q or q1 is function of some variables. Is function of some variables. In the second case, what has been done is, it says there is another function f1 where the dependent variable also has been brought inside. So f1 of q1, comma q2, comma q3, comma q4, and so on qn is equal to a dimensionless constant c. This is another functional relationship between all the dependent and independent variables. In accordance with the Pi theorem, we can establish a non-dimensional equation. This is a non-dimensional and homogeneous equation. How do you establish this non-dimensional equation? If there are n variables involved in phenomenon, like q1, q2, q3, q4 up to qn, all these are the variables, either dependent or independent variables. There are total n variables involved in the phenomenon. And if all these n variables are described by using m fundamental quantities, then you will have n minus m number of pi terms. N minus m number of pi terms. Pi2 is another pi term. So, basing on this Buckingham Pi theorem, we can formulate a non-dimensional equation with another function f2 of pi1, comma pi2, comma pi3, comma pi4 up to what? Up to pi n minus m, because you have n number of variables, m fundamental quantities are there which are being described, and hence n minus m is the number of dimensionless terms. So you can have another function f2 of pi1, comma pi2, comma pi3, comma pi4 up to so on pi n minus m equal to c1. This can be formulated by making use of the Buckingham statement. Each dimensionless pi term is formed. So next question is, how to form this pi1, pi2, pi3? Pi1, pi2, pi3, how do we form this? So these will be formed by combining m variables out of the total number of n variables with one of the remaining variable. So if you have up to m variables, then up to from m to n you have qm plus 1, qm plus 2, up to qn. So the pi terms will be formulated like this: pi1, pi2, pi3, so on. How do we formulate? Choose some of the variables as the repeating variables, like q2, q3, q4, qm, q2, q3, q4, qm. These are all called the repeating variables. In each pi term they will be repeated. M number of pi terms will be repeated, and they will be raised to different exponent variable powers, like q2 to the power a1, q3 to the power b1, q4 to the power c1, and so on. Similarly, a2, b2, c2, next a3, b3, c3. Multiply with one of the remaining terms. This is how the pi terms will be formulated. Let us have a clear and more understanding with the problem what we have solved in the studies class by making use of the Raleigh's method. So we have used Raleigh's method. Now we take up the same problem, flow through an RFIs, using Buckingham method. The various steps that are involved are, you need to identify how many physical quantities are there which are describing the entire physical phenomena. Yesterday already we have seen the discharge Q, depends on the diameter, head, acceleration due to gravity, viscosity, and mass density. So Q, D, H, G, mu, rho, these are all the variables which are used to describe the phenomena. These are all the variables which are used to describe the phenomena. So the functional relationship can always be established among the dependent and independent variables together as Q is equal to function of D, H, G, mu, rho. All the variables are separated by comma. All the variables are separated by comma. Then bringing these dependent variables also into the functional relationship, another function f of Q, D, H, G, mu, rho is equal to a dimensionless constant C. A dimensionless constant C. So what we have done in the first step, we identified in the entire physical phenomena what are the variables involved, which is the dependent variable and which are the independent variables. A functional relationship, a mathematical functional relationship between the dependent and independent variables has been shown. Q is a function of the variables, or function of all the dependent and independent variables would be equal to a dimensionless constant C. Now identify how many number of variables are there in this phenomena. That is what is called N. N is the number of variables used to describe the entire phenomena. So number of variables N would be equal to Q, D, H, G, mu, rho. 1, 2, 3, 4, 5, 6. Total 6 number of variables are there. Total number 6 number of variables are there to describe this entire physical phenomena. Then, how many fundamental quantities are required to describe this? So, to know about that, we need to write the dimensional formula for all these variables. For example, mass density rho. What is the dimensional formula? Mass per unit volume. M L to the power minus 3. That means you have used now M and L. M and L. Similarly, dynamic viscosity M L to the power minus 1, T to the power minus 1. That means you have used M, L as well as T. That so all these 6 terms can be completely described by 3 primary quantities: mass M, length L, time T. So the number of fundamental quantities used to describe all the variables involved in this phenomena is equal to M, which is equal to 3. You have number of variables 6, number of fundamental quantities to describe 3. Number of dimensionless pi terms as per the Buckingham Pi Theorem would be N minus M. In the theorem also we have seen that the entire thing can be expressed exactly with N minus M dimensionless independent pi terms. Dimensionless independent pi terms. So the number of dimensionless terms would be N minus M, 6 minus 3, which is equal to 3. So you have 3 dimensionless pi terms. 3 terms, pi 1, pi 2, pi 3. 3 pi terms are there. So another function f2 of pi 1, pi 2, pi 3 is equal to a dimensionless constant C. Now the question is how to formulate these dimensionless pi terms. How to formulate these dimensionless pi terms. Pi 1, pi 2, pi 3 are to be formulated by choosing some of the variables as the repeating variables. How many repeating variables should be chosen? The number of repeating variables should be chosen equal to the number of fundamental quantities used to describe the phenomena. The number of fundamental quantities used to describe the phenomena. So in this case, the number of fundamental quantities are mass, length, time, 3. So you have to choose 3 variables as the repeating variables. From all these 6 variables, choose 3 variables as the repeating variables to formulate the dimensionless terms like pi 1, pi 2, pi 3. So you need to choose the repeating variables in the second step. So the number of repeating variables must be equal to the number of fundamental quantities. In this case, it is 3. It is 3. So preferably one fluid property, one flow property, and a linear parameter may be chosen as the repeating variables. We come back once again how to choose the repeating variables. But at the moment, to understand the whole concept, let us limit ourselves to choosing one fluid property, one flow property, and one linear dimension as the repeating variable. So among 6 variables that are available, like Q, D, H, G, mu, rho, you choose the repeating variables rho as one of the repeating variable, D, the diameter, and G, the acceleration due to gravity. So these 3 are chosen as the repeating variables. At the moment, please try to understand that one is a fluid property, rho, mass density. and the other is flow property, acceleration, and D, the linear dimension, a linear parameter. So you have rho dg, which are chosen as the repeating variable. As the name suggests, repeating variables. So these variables will be repeated in all dimensionless pi terms. Pi 1, pi 2, pi 3, this will be repeated. So pi 1, rho dg, pi 2, rho dg, pi 3, rho dg. Repeating variables are to be raised to several exponent powers. Several exponent powers. So several powers like A1, B1, C1 are the variables. So rho to the power A1, D to the power B1, G to the power C1. Similarly, this rho dg in pi 2 are now raised to A2, B2, C2. Here rho dg are raised to A3, B3, C3. Followed? Now you got the formulation of the pi terms. So for formulating the number of pi terms, first of all, you need to understand how many pi terms are to be formulated. To n minus m pi terms are to be formulated. In our case, we have total 6 variables, of which m are the fundamental quantity is 3, and hence 6 minus 3 pi terms are to be formulated in this present problem. Pi 1, pi 2, pi 3. Choose 3 variables as the repeating variables among the 6 variables. We have chosen rho dg as a repeating variables. As the name is suggesting that it is the repeating variable, you need to repeat in all the pi terms rho dg, rho dg, rho dg. They are raised to different exponent powers like A1, B1, C1, A2, B2, C2, A3, B3, C3, and then multiply with one of the remaining variables. This is to be multiplied with one of the remaining variable. Your total 6 variables are there, of which rho dg have been taken out. So what else is left now? Q is left, H is left, mu is left. So Q, mu, H multiply with one of the remaining variable. So this is how the pi terms are formulated. What is the next step now? You have to solve each of the pi term, pi 1, pi 2, pi 3. You need to solve by treating them dimensionally homogeneous. And pi 1 is a dimensionless term, first point. Pi 1 is a dimensionless term. Pi 2 is a dimensionless term. Pi 3 also is a dimensionless term. As per the Buckingham theorem, they are all the dimensionless pi terms, independent dimensionless pi terms. So what do you mean by this dimensionless term? M to the power 0, L to the power 0, T to the power 0 is the dimensional formula for pi 1. So take the equation number pi 1 first. For pi 1, write the dimensional formula on the left hand side as well as on the right hand side. For all the variables, write the dimensional formula. Left hand side pi 1, m power 0, L power 0, T power 0, which means that it is a dimensionless term. It is a dimensionless term is equal to rho to the power A1, rho mass density, mass by volume, m by L cube, or m L to the power minus 3, m by L cube, or m L to the power minus 3, to the power A1, rho to the power A1. Next, d to the power B1. What is d? It is the diameter, size of the orifice, a linear parameter, L. The dimensional formula is L. L to the power B1. Then acceleration due to gravity. So L T to the power minus 2 to the power C1 into discharge Q. There is no power for this. There is no exponent for this. Okay. So what is this discharge Q? Discharge volume rate, volume by time, L cube T to the power minus 1. So what you have done now, you have taken one pi term pi 1, and for this pi term, you started writing the dimensional formula for both left hand side and the right hand side. Right hand side you have rho, d, g and q. For all these variables, you have written the dimensional formula. Rho, mass density, ml to the power minus 3, d, that is the size of the orifice, L, and g, acceleration due to gravity, L T to the power minus 2, and the discharge q, L cube T to the power minus 1. Now, what you need to do? You need to regroup the terms. For example, m to the power a1, there is no other m available here. M to the power a1. L to the power minus 3a1 plus b1 plus c1 plus 3. Similarly, for t also you have minus 2c1 minus 1. Minus 2c1 minus 1. So you have got now m to the power a1, L to the power minus 3a1 plus b1 plus c1 plus 3, and t to the power minus 2c1 minus 1. We start comparing left hand side and right hand side, the powers of the like terms. Powers of the like terms. For m, if you compare left hand side, you have 0. Right hand side you have minus 3a1 plus, right hand side you have a1. So a1 is equal to 0. Similarly, for L also, minus 3a1 plus b1 plus c1 plus 3 is equal to 0. For T, minus 2c1 minus 1 is equal to 0. So you have got 3 equations now. You have got 3 equations. And how many variables are there? 3 variables are there. A1, B1, C1. This is the easiest part in this Buckingham method as compared to the Raleigh's method. In the Raleigh's method, in both the problems we have seen, the number of equations are less compared to the total number of unknown variables in the equations. So you don't have a unique solution, but instead you have infinite number of solutions, or you have solved any 3 variables in terms of the remaining 2 or remaining 1 variable in the studies class. But today, in the Buckingham method, you must have noticed that there are 3 equations and 3 unknowns. Anytime whether you take pi 2, you take pi 3, in all the cases you have only 3 equations, 3 unknowns. So number of equations equal to the number of variables. So you will be able to solve the value of a1, b1, c1 because you have 3 equations and 3 unknowns. Similarly for pi 2 also, follow the same procedure. Find the values of a2, b2, c2. Find the values of a3, b3, c3 and substitute those values. Substitute those values because you will get some numericals. a1, b1, c1, some numericals will be there. So substituting those numericals here, you will be able to arrive at or solve for pi 1 value, like pi 1 is equal to q by g to the power half d to the power 5 by 2. Pi 2 mu by rho g to the power half d to the power 5 by 2. Pi 3 h by d. So you got the values of pi 1, pi 2, pi 3. So among these pi terms, the functional relationship can be established. How do you establish the functional relationship? Function f2 of pi 1 comma pi 2 comma pi 3 is equal to a dimensionless constant c1. A dimensionless constant c1. So f2 of what is pi 1? Just now we have seen q by g to the power half d to the power 5 by 2, comma pi 2 mu by rho g to the power half d to the power 5 by 2, comma pi 3 h by d is equal to c1. Now there is one pi term which is consisting of the dependent variable. So in this equation, in this phenomena, the discharge q is the dependent variable which is flowing through the orifice. So the term relating to that can be taken out of the functional relationship. Can be taken out of the functional relationship. So the discharge q is the dependent variable. So identify this term. Correspondingly, q by g to the power half d to the power 5 by 2 is equal to some other function f3 of mu by rho g to the power half d to the power 5 by 2, comma h by d, comma h by d. Or q is equal to, the discharge q is equal to g to the power half d to the power 5 by 2 into some function f3 of mu by rho g to the power of d by 3, d to the power 3 by 2, comma h by d. So now you establish a relation for the dependent variable q with all the other independent variables like d, g, h, mu and rho. Okay, so q is equal to this. So by making certain mathematical manipulation here, you will be able to get in like yesterday's form. You multiply with pi by 4 into root 2 and divide with pi by 4 into root 2, so that you will be able to get a, small a, the cross section area of the orifice into root 2 gh into function of something which is equal to the quotient of discharge CD. So this procedure is now established here in a very stepwise manner. So the procedure which just now we have seen in this problem, like flow through orifice, is now outlined here in a stepwise procedure. In the step 1, list all the variables, list all physical quantities or variables involved in the phenomena, n variables. Note their dimensions and the number m, which is the number of fundamental or primary quantities available. That means you are trying to identify the value of n is equal to 6, something like that. The value of m is equal to 3, mass and time. There will be n minus m pi terms. Select m variables out of these which serve as the repeating variables. Rho, d, we have taken up like rho, d and g as the repeating variables. So these variables should be, how to select these repeating variables? Now the procedure is given here. We told you that one fluid property, one flow property, and one linear dimension may be taken, right? So while choosing the repeating variables, you need to look at this careful. None of them is a dimensionless term. You should not choose any non-dimensional parameter as a repeating variable. For example, efficiency eta or coefficient of discharge. These are all dimensionless terms. So don't choose any dimensionless term as a repeating variable. No two variables have the same dimensions. You cannot choose two variables having the same dimension. In the previous problem, if you see, Q, D, G, H, rho, and mu are the parameters. What is H? Head of water. So this will have the dimension of L. H in meters, no? So the dimension is L. Similarly, D, the diameter of the orifice. This is also having the dimension of L. So you should not choose any two repeating variables having the same dimension. You cannot choose both diameter as well as head as the repeating variables. You can choose only one among them. Similarly, they themselves do not form a dimensionless parameter. You should not choose something like a speed and time, t to the power minus 1 and t. You should not choose as a repeating variable. All the m fundamental dimensions are included in the variables, should not be taken as the repeating variables. There is a small change here. All m fundamental dimensions are included. This is one part. All m fundamental dimensions are included. That means while choosing the repeating variables like rho, d, and g, if you look at the dimensional formula for all the three terms, you should be having all mass, length, time to describe these parameters. So that also you taken that. Then one more important point is here is dependent variable should not be chosen as a repeating variable. Dependent variable should not be chosen as a repeating variable. So in our case, what is the dependent variable? Dependent variable, the discharge Q. So Q should not be chosen as a repeating variable. You should not choose two repeating variables having the same dimension. You should not choose a dimensionless variable as a repeating variable, and they themselves should not form a dimensionless parameter. And you should choose all the three three repeating variables in such a way that the m fundamental quantities must be available in the three, like mass, length, time must be completely there in those three repeating variables. Dependent variable should not be chosen as a repeating variable. Usually a characteristic linear dimension. In our case, we have taken the size of the orifice. A characteristic velocity or a flow property like acceleration due to gravity, and a characteristic fluid property, mass density, are chosen as the repeating variables. So the procedure is so clear that how to formulate these pi terms is given clearly here. You have to choose the repeating variables, and you need to be very careful by choosing the repeating variables. Dependent quantity should not be chosen as a repeating variable. A characteristic linear dimension, a characteristic velocity, a characteristic fluid property may be chosen as the repeating variables. After choosing the repeating variable, you need to write the general equation for different pi terms. How do you write these pi terms? Pi1 is equal to rho d g, raise it to the powers a1, b1, c1 into one of the remaining variable like q. So this is how you need to formulate, develop the pi terms. Similarly pi2, similarly pi3. Then write the dimensional equations for each of the pi terms, solve for all the pi terms, then write the final general equation. Identify the dependent variable component, dependent variable term, take out of the functional relationship, and identify what is the value of q is equal to. Okay, so this is how the outline procedure is. In order to obtain this final general expression in a very required manner, we have seen in the earlier case it is not in a very standard form. Q is equal to CDA root to 2GH. In that form you have not got, but you have got in a different form. So to get that in the desired form, you can do certain things. If a quantity is dimensionless, it is a pi term without going through the above procedure. For example, efficiency eta, it is a dimensionless term that can be chosen directly as a pi term. If any two physical quantities have the same dimensions, their ratio also will be one of the pi terms. So you have two physical quantities available in the phenomena. and both are having the same dimension. Take out once again our previous problem, flow through the RFIs. H, D, both are having the same dimension. So H by D becomes a pi term. We already proved it also. H by D, we have got one term. Pi 3 is equal to H by D. This is what we have obtained. Any pi term may be replaced by any power of the term. This is another flexibility available in these pi terms, including the fractional powers. Any pi term may be replaced. For example, if you have pi 1 may be replaced by pi 1 to the power minus 1, pi 1 to the power minus 1, which means that whether you use h by d or d by h, there is no change. There is no change because you are only establishing a functional relationship. Establishing only a functional relationship. So pi 1 may be replaced by pi 1 to the power half, pi 1 to the power half, pi 1 to the power minus 1, pi square, anything can be. And one term may be replaced by the other term there. Any pi term may be replaced by multiplying by a numerical constant. Pi may be replaced by 3 pi or simply pi or a half pi, so on. Similarly, pi 1 may be replaced by pi 1 into pi 2, pi 1 by pi 2, and so on. Pi 1 into pi 2. Pi 1 may be replaced by pi 1 into pi 2 or pi 1 by pi 2 and so on. So this is how there is flexibility because we are establishing only a functional relationship between the dependent and independent variables. Okay, so we try to take up a few problems quickly, and then you need to work out these problems also by taking a pen and a paper right now. So one problem, maybe a few problems on Raleigh's method, few problems on Buckingham Pi method, both we see. List all the variables that may influence the motion of a moving body fully submerged in a fluid, and by dimensional analysis, there is an expression for the resistance to the motion of that body. So you are trying to take a submerged body. So this submerged body is influenced by several parameters like length, velocity v, viscosity of the fluid, mass density of the fluid rho, resistance to the motion, which is a dependent variable. So R is function of all the other parameters. L, length. So its dimension formula is L, capital L. Velocity v, so Lt to the power minus 1. Viscosity mu, m L minus 1 t to the power minus 1. And mass density rho, ml to the power minus 3. And resistance to the motion, something like force, resistance or force. So this will be force dimension formula, mass into acceleration, mlt to the power minus 2. mlt to the power minus 2. Now we have arrived at the dimensions of all these variables. R is a dependent quantity and L, V, mu, R are the independent variables. And all these variables are described by three fundamental quantities: mass, length, and time. Altogether you have MLT. So the functional relationship would be R is equal to function of L, V, mu, rho. Else another function f of R, L, V, mu, rho would be equal to a dimensionless constant C. How many variables are there in this? R, L, V, mu, rho. 1, 2, 3, 4, 5. So the number of variables involved in this physical phenomena n is equal to 5. And the number of fundamental quantities you have seen, mass, length, time, 3. So n is equal to 5, m is equal to 3. Number of pi terms, dimensionless pi terms will be n minus m, 5 minus 3. 2 pi terms are to be formulated. Pi 1 and pi 2 are the pi terms. So you need to choose the number of repeating variables being equal to the number of fundamental quantities used to describe the phenomena. So the number of fundamental quantities is 3, and hence the number of repeating variables also must be 3. So you need to choose 3 variables as the repeating variables. We should not choose dependent variable as a repeating variable. I repeat once again, we should not choose dependent variable as a repeating variable. So in this problem, resistance R is a dependent variable, so it should not be chosen. Then you have 4 other values are there, variables are there: mass density rho, length L, velocity V, and viscosity mu is there. So either mass density or viscosity may be chosen. For the present case, I have chosen rho as the repeating variable, and hence you have rho, L, V as the repeating variables. So to formulate, pi 1 is equal to rho, L, V, pi 2 is equal to rho, L, V, which are raised to different exponent powers like rho to the power A1, L to the power B1, V to the power C1. multiply with one of the remaining variables. The remaining variables are resistance R, and in the second case viscosity mu. So you got now the pi terms formulated, pi 1, pi 2. You need to solve for pi 1 and pi 2, treating them as dimensionless terms. So pi 1 is equal to, write all the dimension formula. Pi 1 is equal to rho to the power A1, rho mass density ml to the power minus 3 to the power A1 into L length. So it's a linear dimension, capital L to the power B1 into velocity V, LT to the power minus 1 to the power C1 into the resistance R, MLT to the power minus 2. Left hand side, pi 1. What is pi 1? It's a dimensionless term. So m power 0, L power 0, T power 0 is equal to, grouping all the terms, m to the power A1 plus 1, L to the power minus 3A1 plus B1 plus C1 plus 1, T to the power minus C1 minus 2. Now, compare the powers of the like terms. If you compare m and m here, m on the left hand side, m on the right hand side. Here the power is 0, here the power is A1 plus 1. So A1 plus 1 is equal to 0. One equation is formed. Minus 3A1 plus B1 plus C1 plus 1 is equal to 0. Second equation is formed. Minus C1 minus C2 minus 2 is equal to 0. Third equation is formed. So you have three equations, and you have to solve for these three equations because you have three variables, A1, B1, C1. Solve for A1, B1, C1 from these three equations, three unknowns. Number of unknowns is equal to the number of equations. Unique solution is obtained. Pi 1 would be equal to R by rho L square V square. Similarly, take pi 2 and you get the value of pi 2 being equal to mu by rho L V. So f of pi 1 minus pi 2, pi 1 comma pi 2 is equal to C. Pi 1, pi 2 substitute here, you are getting R by rho L square V square comma mu by rho L V is equal to a dimensionless constant C. Now, R is the dependent variable. So the term pertaining to the dependent variable must be taken out of the functional relationship. So R by rho L square V square is equal to some other function f dash or f1 or phi or psi, whatever may be the functional relationship of mu by rho L V, or R is equal to rho L square V square into f of mu by rho L V. So you now establish a relationship between the dependent variable R and all other independent variables. One more problem, let us see. If the capillary rise H depends on the specific weight gamma, surface tension sigma of the fluid, and the radius of the tube is smaller, show that H by R is equal to psi, is also a functional relationship, psi of sigma by gamma R square. Sigma by gamma R square. Look at here, the capillary rise H, this is the dependent variable which depends on. So this is a dependent variable. What are the independent variables given? The specific weight gamma, surface tension, sigma of the fluid, and the radius of the tube R. Radius of the tube R. So total how many variables are there now? H, gamma, sigma, and R are there. R. So total 4 variables are there. Total 4. Of course, acceleration due to gravity is not given here, but you need to take this also. If it is not there, it will come out as 0 towards the end. Acceleration Lg is there, Lt to the power minus 2, because this is not location specific, So you need to take the G also. Then the value of n, and m is equal to 3. N minus m. Number of pi terms will be 2 pi terms. Pi 1, pi 2. F of pi 1 comma pi 2 must be equal to C. Formulate the values of pi 1 and pi 2 equations. Pi 1, pi 2. Choose 3 repeating variables. Gamma, R, and G are chosen as the repeating variables here. Gamma, R, and G are chosen as the repeating variables. Accordingly, you got pi 1, gamma to the power A1, R to the power B1, G to the power C1 into H. Similarly, pi 2 will be gamma to the power A2, R to the power B2, G to the power C2 into sigma. Then you got the value of pi 1. Treat this pi 1 as a dimensionless term. Write the dimensional formula for right hand side as well as the left hand side and solve for it. So pi 1 is equal to H by R you got. Similarly, pi 2 would be equal to, what is that pi 2 you got? Sigma by gamma R square you got. Gamma R square. So f of pi 1 comma pi 2 is equal to C. Pi 1 comma pi 2 is equal to C. So you got f of H by R comma sigma by gamma R square is equal to C, or H by R is equal to psi of sigma by gamma R square. You can understand one point here. What we have done in this problem is we have taken G, acceleration due to gravity, also is one of the repeating variable. But towards the end of the result, you have not got. That means in both the cases, the value of G has become 0. It has become 0. So value of G correspondingly C1 has become 0 here. Similarly, value of G C2 has become 0. So accordingly, you got the values of pi1 and pi2. So if you take only two variables there as the repeating variables, then also you can solve this problem. You can solve this problem. One more we'll see. The efficiency heat of a fan depends on the density rho, viscosity mu of the fluid, angular velocity omega, diameter capital D, and the discharge Q. Obtain a functional relationship for eta in terms of the dimensionless parameters. This is the discharge capital Q, and obtain a functional relationship for eta in terms of the dimensionless parameters. So what are given here? Efficiency eta depends on so many parameters. So eta is a dependent quantity. What are the other parameters given? Mass density, viscosity, angular velocity. So this will be something like so many revolutions per minute and speed. So T to the power minus 1 diameter. Then discharge Q, L to the power 3, T to the power minus 1. Identify how many variables are there. N is equal to 6, M is equal to 3, N minus M, number of pi terms will be equal to 3, pi1, pi2, pi3. Choose repeating variables, rho, omega, D are chosen as the repeating variables. So rho to the power A1, omega to the power B1, D to the power C1. Here A2, B2, C2, A3, B3, C3. Multiply with one of the remaining terms. Remaining term is eta, mu, and the discharge Q here. The discharge Q here. Okay. Solve this pi1, pi2, pi3, treating them as the dimensionless terms. So when you solve this, you may note here one very interesting point. P1 is equal to rho to the power A1, omega to the power B1, D to the power C1. So start writing into eta. Start writing the dimensional formula for this. Pi1 dimensionless term, m power 0, L power 0, T power 0. Rho mass density, m L to the power minus 3 to the power A1. Omega T to the power minus 1 to the power B1. D, the diameter L to the power C1 into eta, the efficiency m power 0, L power 0, T power 0. M power 0, L power 0, T power 0. So when you just group all the terms and compare, you will be getting A1 is equal to 0, B1 is equal to 0, C1 is equal to 0, which indicates that pi1 is becoming simply equal to eta. This is what has been given while we have listed out the outline procedure. What was listed there? If any of the term is a dimensionless term involved in a physical phenomena, it is going to be a pi term without following the procedure. Even if you don't follow the procedure, you can straight away say that pi1 is equal to eta. You can straight away say that pi1 is equal to eta. Solve for pi2. You follow the same mathematical procedure. M power 0, L power 0, T power 0 is equal to rho, omega, D, A2, B2, C2 multiplied by mu. Then solve for A1, B1, A2, B2 and C2. Accordingly, you got pi2 is equal to mu by rho omega D square. Similarly, pi3, if you solve Q by rho D square. Substituting all these values here, f of pi1, pi2, pi3 is equal to C. F of eta, mu by rho omega D square, Q by omega D square is equal to C. In this, we need a functional relationship for the dependent variable eta. So take out this eta from the functional relationship. So eta is equal to some other function psi of mu by rho omega D square, Q by omega D square. Okay, so this is how you need to look at it. So one more problem also is given. So in this problem, if you note, I'll just read out this problem again. Obtain an expression for critical depth of IC in a triangular channel. So you need to find the expression for the critical depth of IC in a triangular channel, which depends on the discharge Q, acceleration due to gravity G, and the channel angle theta. So just follow the simple mathematical procedure like critical depth of IC, dimensional formula L, discharge Q, L cube T to the power minus 1, and gravitational acceleration G, L T to the power minus 2, and channel angle theta, L power 0, T power 0. In all these cases, you don't find M. Have you noted? You don't find mass, length, time. M is not there. So how many fundamental or primary quantities are there to describe the entire phenomena here? Only 2, L, T. That's all. So in this case, the value of M is 1, 2, 3, 4. whereas the value of n is 1, 2, 3, 4, but the value of m is only two primary quantities, L and T. M is not there. L and T. M is not there. So the value of m is equal to small m is equal to 2, and hence n minus m, 4 minus 2, 2 pi terms will be there. Choose any two repeating variables, discharge Q and G are chosen as the repeating variables. Q and G are chosen as the repeating variable. YC should not be chosen. YC is the critical depth which depends on these parameters. So solve for pi 1, solve for pi 2, and f of pi 1 comma pi 2 is equal to C, and hence Q, I mean the critical depth of YC is equal to Q square by G into function of theta. Into function of theta. Okay. Similarly, one more problem on the pressure drop. So suppose if you have a pipe flow where there is an obstruction, so there will be drop in pressure. So this drop in pressure depends on several parameters like diameter, average velocity, mass density, viscosity, etc. And you need to find an expression for or a functional relationship for the pressure drop delta P. Write all the dimensional formula for all the parameters, and then identify the value of n, the value of m, and then number of pi times n minus m is equal to 3. Then pi 1 comma pi 2 comma pi 3 are to be computed. The functional relationship will be f of pi 1 comma pi 2 comma pi 3 is equal to a dimensionless constant C1. So you need to identify, formulate pi 1, solve for pi 1, formulate pi 2, solve for pi 2, and formulate pi 3, solve for pi 3, pi 1, pi 2, pi 3. So choose in the repeating variables rho, v, d, multiply with one of the remaining variable delta P, mu, and d. So they are raised to the powers a1, b1, c1, a2, b2, c2, a3, b3, c3. So pi 1 will be equal to rho to the power a1, b to the power c1, d to the power, b to the power b1, d to the power c1 into delta P. Write the dimensional formula. Solve for pi 1. Similarly, for pi 2, pi 1 is equal to delta P by rho v square. Similarly, for pi 2, mu by rho v d. For pi 3, d small d by capital D. So f of pi 1 comma pi 2 comma pi 3 is equal to C. Substitute for pi 1, substitute for pi 3, substitute for pi 2. Identify the term which is containing the dependent variable delta P by rho v square. Take out from the functional relationship. So delta P by rho v square is equal to some other function f1 of so mu by rho v d comma d by d. Okay. So this is one more problem. So these problems can be solved, but please try to note that interestingly, for any of these fluid flow problems, we have not used our conventional formulae, like we are not using the discharge equation, we are not using the continuity, we are not using the Bernoulli equation, we are not using the momentum equation. So conventional method is not followed, and we have followed a simple mathematical routine procedure. This procedure is like a Buckingham Pi method has been adopted. So this is one of the powerful dimensional analysis techniques to solve the problems of the fluid flows. So you have Raleigh's method on one side, you have Buckingham method on other side. If you just compare both the methods, if you try to compare, both the methods are definitely useful for getting the solution for the fluid flow problems using this technique, using the respective techniques. But as compared to the Raleigh's method, the ease that is available in the Buckingham method is that every time, let it be pi 1, let it be pi 2, or let it be pi 3, every time you have a dimensionless term which is having the number of unknowns equal to the number of equations. So unique solution you obtain. But only the difficulty is pi 1 is to be solved separately, pi 2 is to be solved separately, pi 3 is to be solved. So it is a little laborious. But you will be able to get the unique solution every time. But in the case of Raleigh's method, you may observe that only is not laborious, because you will be getting only one time the number of equations and number of unknowns. But the complexity involved there is that in most of the cases, the number of variables involved and the number of unknowns, they are not equal. Number of variables involved in the phenomena and the number of unknowns are not equal. So you need to solve some of the variables in terms of the remaining variables. So that is the complexity available in the Raleigh's method, but the laboriousness available in the